Okay, when you want to, for example, buy something online, and you send your credit card information to, there's going to be some company that manages that, whether it's VeriSign or if it's, there's different companies that their job, all they do is they safely transfer secret information that's really important secret information related to bank accounts, social security numbers, etc. from one place to another online in a way that's not hackable or breakable. So when you do that, if you're on your browser and you're going to buy something online, a couple things you want to know. First of all, you want to know that it's being done in a way that's good. That you on your browser you need to have like 128 bit encryption or better. Is a good idea. But then also that the company is using, that you're buying this from, is using some service that's reputable, like VeriSign, or that it's, so it's being done in a way that makes sense. A lot of times if you look at the top, if it's in, there'll be a little logo up there that tells you that this is safe, that this is done in a way that meets all the standards and requirements. But how does that work? How does that work? So if you want to take your string of credit card numbers and you want to encrypt those in a way that's not going to make any sense to anybody that's trying to steal that information, but then will make sense to somebody on the other end of the transmission, how do you go about doing that? Okay, because computers can decrypt things pretty easily. Computers are good at looking for patterns. They can try lots of different patterns very quickly and see if they get anything that makes sense. If they start to, you know what I mean? So there are ways that hackers have tools now that allow them to do lots of mathematical analysis of this stuff and try to get your secret information. Or maybe if you wanted to send a secret message to an agent that's behind enemy lines and you got some important information to give them, how could you encrypt a message, send it to them, so that even if it's intercepted, it's not going to mean anything to the enemy intelligence. They're not going to understand what you're trying to say. Okay, that's what we're going to get to. All right, to get there, I have to introduce something new, a new matrix thing. And I want to remind you about something we talked about last week. If we talk about some properties of real numbers that are going to be important for matrices, there's two of them. One of them is the identity property. Right? So we know that there's an identity number for each operation that we do. For addition, what is the identity number? In other words, some number A plus what gives me back the same answer? 0. So 0 is the identity number for addition. Right? That's what goes there. Okay? What is the identity number for multiplication? 1. Okay? Okay, now the way you get an inverse, remember, and I know we already talked about this, I want to review this. The way you get an inverse is you then say, okay, now some number plus what, and that's going to be the inverse, whatever goes in there, equals the identity number, right? So for addition, a plus the inverse should equal 0. For multiplication, a times the inverse should equal 1. So what is the inverse for addition? How do I opposite? Good. Okay, so the additive inverse is just the opposite of a number, right? Mm-hmm. For multiplication, what is it? Reciprocal. Reciprocal. Good. Okay. So for multiplication, the inverse is just the reciprocal of a number, right? Okay, now why is this important? Well, here's kind of why. On the assignment, it's a very, very short assignment that I'm going to give you. It won't take you long at all. You're going to get some problems like this, for one thing, where you're asked to solve a matrix equation. Now, what does that mean? Okay, that means if you have some matrix times capital X equals some other matrix, what do you suppose that capital X is? Another matrix. Yeah, it's what we might call the variable matrix. It's what we're trying to find, the mystery matrix, right? How do I isolate that X? How do I get the X by itself? Okay, you'd want to divide, wouldn't you? If we were doing this with regular numbers. Yeah, exactly. If I had something like with numbers, it might look like 2x equals 10, because that's really just the matrix equivalent of some number, right? That's the matrix equivalent of some other number. And when we're solving this using real numbers, we just divide both sides by 2 to get the x by itself. But the problem is, you might remember me saying, you can't divide matrices. Division is an operation that is not defined for matrices. Okay, so we have to think about this a little differently. It's going to accomplish the same thing, but it's a slightly different concept. So how could we go about that if division is off limits? How could we solve if a is a number and b is a number, and these are just real numbers, and I want to solve for x? Without dividing by a, how can we get rid of the a? Good. We're going to multiply by the inverse, right? Because multiplying by the inverse gives us back the identity number for multiplication. That's a good idea, because look what happens. If I were able to get back on this side, if I could just get the identity number for multiplication, which is a 1 times x equals something over here, that's my answer. 1 times x is just x, right? So that's how I get my answer. Well, how do I do that? I get this 1 by multiplying the number by its inverse, right? That always gives you back 1. So we're going to, and I can do that in any order with regular real numbers. So I'm going to multiply both sides by the multiplicative inverse of a. That's a mouthful. So just the inverse for multiplication. And then that's going to give me 1 over a times a gives me 1. On the other side, if I multiply straight across, what's 1 over a times b? B over a. Okay, so, and that's how we get our answer of b over a, b divided by a, right? Okay, we can do the same thing for matrices. Whoops. So if we call, let's just say we're going to call this matrix right here, this guy, we'll call matrix A. Gotta give myself a little room here. Okay, we'll call this one matrix X equals, and we'll call this one, how about matrix B? Yes, ma'am.
So the only way that you could get the answer, the negative sign, is if X.
Yes. Yep. Exactly. Yeah. X is a matrix. Yeah. In fact, we could even predict what the dimensions of that matrix are going to be, can't we? If we think about this, what are the dimensions of this guy right here?
2 by 2.
2 by 2. Okay, so if A is a 2 by 2, and B is a 2 by 3, very good.
2 by 2.
2 by something.
What's it going to have to be?
2 by 2.
2 by something.
2 by something, right? Because we know that the inside dimensions have to match up. So we know that that first one has to be a 2, right? Because those have to be the same when we're multiplying matrices. Okay, what's the second dimension going to be? It's got to be a 3. Are you guys getting this? Okay. That's got to be a 3, because look, because we know that this one, the outer dimension of the product, becomes the first dimension of the resultant matrix, and that 3 ends up there, right? And those just have to match up. I mean, not that that's a big deal. We'll figure out what it is, but it has to be a 2 by 3 matrix. Now, how are we going to find out which one? Well, get rid of that now. Okay, what did we just talk about? How could I isolate matrix X? How am I going to undo multiplying by A? Okay, now for matrices, it's not just the reciprocal. It's much more complicated for matrices. And honestly, I'm not even going to go into, if we have time later, I'll do this, but I don't think it's a big deal. I'm not even going to go through how you generate an inverse matrix for now, because you're not really going to do it anyway. You can do it on your calculator. But just know that there is this thing called an inverse matrix, which accomplishes the same thing as a reciprocal does for real numbers. Can you guys put those hats away, please? Thank you. So we're going to multiply by the inverse of A, which we just write like that. Remember that negative 1 power doesn't mean it's to the, it looks like negative 1 power, but it's not. It doesn't mean 1 over A or A to the negative 1. That means inverse, right? So we're going to multiply A by its inverse. Now remember, with matrices, you got to be a little careful with this. Remember that we said matrix multiplication is not commutative. In other words, we know that matrix A times matrix B is not equal to matrix B times matrix A, right?
Yeah.
So the order in which we multiply is important. So I'm going to multiply from the left, and that sounds a little weird that we have to specify that. We're going to multiply matrix A from the left by its inverse. And being as this is an equation, we have to do the same thing to whatever's on the right. We have to multiply this matrix B by the inverse of A from the left. Same order. Okay? Because remember, that matters with matrices. The order of the factors, order in which you multiply the matrices, makes a huge difference. So then this becomes over here. I got to give myself a little more room. So I'm going to get my matrix B. Oops. Gets multiplied from the left by the inverse of A. Now, what did we say if we go back last week? What did we say we got if we multiplied, well, what was the matrix equivalent of the number 1? Do you remember that? Yes, sir. Mr. Gary.
1, 0.
Oh, okay. Yeah, it was that weird looking matrix that had all the 1s and the 0s in it. What do we call that?
Determinant.
No, because we did talk about determinant, but that's what we call the identity matrix, right? And remember, on your calculator, you can just pull those up. Like if I wanted to, for example, I could go into the matrix screen, and I can go to math, and there's identity 5. If I want to do, they're always square. The identity matrix could assume any size. It doesn't make any difference. Whichever size you need is the one that you pick. If I wanted, for example, a 4x4 identity matrix, there it is, right? That's the matrix equivalent. That's the 4x4 matrix equivalent of the number 1. If I wanted a 3x3, it would just be the same pattern, but only 3 rows by 3 columns, right? So then we know that these two combined always give us the matrix equivalent of 1, which we just call capital I for identity matrix. So we get I times X on this side equals this stuff. A inverse times B. And the identity matrix times another matrix always gives you back what?
Matrix.
Yeah. The identity matrix is literally just preserving the identity. So I times X is just our answer. That's just X, what we're looking for, right? And so our shortcut then, right, we know, and this is literally how you can think of it when you're solving matrix equations. The matrix equivalent of dividing is multiplying from the left by the inverse. That's it. Right, so we know then, now in the future, we know that when we have a problem like this, if I want to solve for X, I'm just going to multiply this matrix on the right by the inverse of matrix A from the left. Okay? How do we do that on our calculators? Let's look at this and see. So if we want to do this on the calculator, we'll just go in and we'll call this matrix A, right? Okay, so we'll call that matrix A. And I've already, what are the odds of that? I've already got it in there. So 2, -9, -3, 6. There's matrix A. I'll call this matrix B. There it is, right? Okay? And all I have to, yeah. And all I have to do then, I know what the answer is going to be. X is just going to be the inverse of A times B. So I don't even have to write down the inverse matrix. I can just let the calculator do it by calling up the inverse notation. So we go second matrix A, inverse, which is the button right in front of the matrix screen, right?
That's handy dandy.
How about that? Yeah. So A inverse times B. There it is.
And that's your answer?
That's your answer.
That is so hard.
Yeah, it's not hard, is it?
Yeah.
Okay, so now, what's that? Yes, you could. How could you check it?
You just plug it in.
Plug it in. Yeah. So if I took A times that, I should get that answer. So you could check it. Yeah. Okay. Now I could make this a little harder, and I just might. What would you do if you had one like this? Now I'm not going to write all the numbers in, but just say that we've got some matrix with numbers that we're calling matrix A. Matrix A times matrix X. Okay, what do you think? If I want to solve for X.
Add zero.
Ah, okay, good. This is just like you would with real numbers. We're going to subtract B from both sides, right? That's normal. That's no big deal, subtracting matrices. The only weird part then is dividing by the A just becomes multiplying from the left by the inverse, right?
Right.
So what's that? If we look at that in a couple steps then,
So we're trying to find that.
yes, you're solving for X. So you get AX equals matrix C minus matrix B, right? Okay, now this is the part that's a little bit, now how am I going to indicate on my calculator that I want to multiply that stuff by A inverse from the left? Parentheses, exactly. Okay, it works just like you'd anticipate. So matrix X just equals A inverse times the quantity matrix C minus matrix B. How would we do that on the calculator? Very simple. You would just plug in matrix A, matrix B, and matrix C from the original problem. And then you would just ask your calculator to do that. Hit enter, and it's going to give you the answer.
Can you show that?
Sure. Okay, so yeah, I'll make up a simple one. So let's say we have,
Oh, what did you just do?
okay, so try that. Solve that one. You have calculators and try solving that one.
Okay, so.
You just explain how to do it. So it's not really tricky.
Yeah, it's not. It's really not.
I'm gonna do the part action.
Okay, so there's, put matrix A in. Put matrix B in.
You're gonna be weird.
Put matrix C in. Okay, so whether you have all those in there, I'll just show you how you get that answer. So would you agree that this is just like this one up here? If I want to get x by itself, I'm just going to subtract matrix B from both sides, right? And then multiply that multiply that quantity from the left by the inverse of A. So all I have to do is this.
Oh wait, I need to do C.
Oops. There's C. Okay.
Yeah. How do you change the cursor so it's not like in the right?
Second insert.
So what do you do? So now you do.
Okay, so once I get those in, then we're just going to quit, and we're going to go A inverse, right, times the quantity.
You don't have to put.
Wait, how do you do it? Oh, yeah.
Say it again.
You don't have to put the signs, right?
You don't. Oh, you may not have to. You probably don't have to. I always just do. C minus B. Matrix C minus. Right? Everybody see that?
Yeah.
It's going to follow order of operations. Calculator's smart. It's going to know to work in the parentheses first and then do the product. And so that's your answer.
Why did I get? No.
Okay, so. Oh, yeah. Oh, wait, yeah.
James got it. Yeah, I did.
Oh wait, yeah.
Okay, so the other kind of question I'm going to give you, listen please. The other kind of question I'm going to give you is, I'll give you an example here. I'm going to give you a random, I'm going to give you a key for encoding a matrix. I'm going to give you an encryption matrix, and you're going to have to decode this special secret message that I sent out to you on your assignment. Okay? A couple Thanksgiving messages from Mr. Roy.
I know. It'll take a while. Yes.
So here it is. So here's how we do this. So if we want to, let's say we want to send a secret message, we're gonna, and this could be however you want to set it up. This is the way we're gonna do it. So these are the way that the letters are gonna be transformed into numbers. And you can have, I mean, like I say, as long as you just have some routine for doing this, doesn't matter. So let's build one real quick here. Let's just say Happy Thanksgiving. How about it?
You should use that one on the thing.
No.
It'll say I love you.
Okay, yeah, that's gonna be too long. I'm gonna do something shorter for now. I'm just gonna say.
Just say
Just
turkey.
say.
Just say shoot.
Okay. There's our quick message.
At least know where you stay.
Okay, so if we want to encrypt this, then all we have to do is we have to decide how big is our encryption matrix going to be. I'm just make it a 3 by 3, and it could be any size. We'll make it 3 by 3, and then we're just going to turn these. First, we turn all the letters into numbers. So you read these off as I go. You look up here and tell me what's an L.
0. 19. 7. 8.
Well, it's got 26 for space.
8.
18.
26. 5.
20.
13.
Oh, 13?
Yes.
Okay, so now we're going to collect these. We're going to build what we might call a collected column matrix. We're going to turn these into just 3 by 1 columns. We'll take the first 3 and we'll build a column. If we know we're going to be using a 3 by 3 encryption matrix, we need to have the same number of rows as our encryption matrix dictates. So 3 by 3, we want 3. So 12, 0, 19. And then we'll just push all these columns together into one big matrix. It makes it easier. So then the next one would be,
And we always do rows first, right?
you're going to do, well, okay, but we're actually putting these in as columns now. Yeah.
But doesn't that go against the whole thing?
Well, okay, but all we're doing, not really, you'll see in a second, because all we're really doing here is just building some matrix, and then we're going to multiply, same as always, same as we've always done.
Oh.
Okay, so this is just, we're building this message matrix, we'll call it.
Wait, how do you figure out the message though?
Well, that's what I'm gonna tell you. Okay. So then keep going. After 8 comes
18,
20, 13, and then we'll do 26 for a space at the end. Does that make sense? Because if you know if you have spaces at the end, you just ignore them. So there's our message matrix. Okay. Right. Now the encryption matrix is going to be one that you would be randomly given. So if you were sending credit card information over the phone, the people that were sending that information would, in some other transmission, they would have sent what for that particular, there's some other code that's maybe not a matrix code. So for that minute of that day, there's going to be, this is the encryption matrix that gets used. Just some random one is generated, and that's what it is. But I'm just going to give you one. So we'll say,
How long does it take you to make these videos?
these take a little while. Yeah. That's not us. Yeah.
Wait,
Okay,
we have
so-
an assignment this
So the encryption matrix E, we'll just make it pretty simple. We'll just make it like 1, 3, -2, 5, -4, -1, 3, 2, 7. How about? Okay? Just random, but that's what we're going to use. So if I want to create then, okay, listen, I'm getting real tired of this. Okay, so if I want to create the encrypted matrix, what do you think I'm going to do? Any ideas?
The index.
Okay, to encrypt it, I'm just going to multiply by this one. And I'm going to multiply. Which one has to go first? If we call this matrix M and this is matrix E, there's only one way that those will multiply.
With that one.
Yeah, this one has to go first, doesn't it? 3 by 3 times 3 by 5 would work, wouldn't it?
Wait, 3 by 5.
Is that 3 by 4? Sorry, 3 by 4. Yep. Okay, so we're going to generate, we're just going to do, if we call this matrix M, we're just going to do E times M. Okay, now I've got this cool little thing that I can attach. If you want me to, I can attach this to the questions I'm giving you to do these. This little computer algebra system I've got rigged up for you.
Whoa.
Yeah, this is kind of cool. You'll like this. Okay, so what this is. Okay, so this allows you, look at this thing for just a second. I'll put this on there sometimes so you don't have to always use a graphing calculator. If you look at these tabs across the top, you can do all kinds of stuff, but in particular, the matrix tab on here is pretty useful. So we can input a matrix, and then we can take inverses and do all kinds of stuff with matrices. So if we want to create, for example, if we want to do this, if we want to do matrix E times matrix M, well, let's just put in matrix E, first of all. So I'll go up to matrix, and then it'll ask me how many rows and columns. So it's 3 by 3. And watch what it does. You're going to like this.
I like it.
3 by 3, and then it just builds this little template. And all you have to do is just put the entries in there. So read them off to me. What's E? 1.
3, -2, 5, -1.
Oh, that's too many people saying it. One person say it for me. Did I mess that up already?
No.
-4. Okay, who's doing it? Somebody raise your hand. Quick, quick. Who's doing it?
Okay,
-1,
Okay, after -4,
yeah.
-1,
3, 2,
Last row is number of the day.
7. Okay, perfect. So there's E times, and then I want to do a 3 by 4, right?
Yeah.
So we'll go here, 3 by 4. And now I want matrix M, so read that off to me, somebody. 12, 7.
18, 20, 0, 26, 26, 13.
How'd I get 220?
There's spaces, because you go down. There's spaces.
Oh, I got you. Yeah, never mind. I got you. Keep going.
19, 8, 5, and 26.
Okay, so if I multiply those, you see that this guy over here, that's the encrypted matrix. So that's the matrix that I would be sending out to you guys. I didn't want anybody else to be able to understand, right? And now think about the number of possibilities there are for this. Think about the number of different ways that we could encrypt this. if I'm just even, this is pretty minor league, but if I were just to say, like I did on the assignment, if I just randomly choose integers between -10 and +10 for my 3x3 encryption matrix, think about that. That's 21 possibilities. -10 to +10 is 21 different digits I can choose from. 21, and there's 9 entries in there. 21 to the 9th. 21 to the 9th is almost a trillion. There's almost a trillion different choices that you could make to that matrix. That's pretty much unbreakable, isn't it? And you don't know what size encryption matrix we use. Because all you're going to see in the field is, you wouldn't see this as a matrix. Honestly, what you would see is just a string of numbers that you would have to put into a matrix. So the nefarious types out there trying to intercept your credit card information, they wouldn't know what the size of the matrix was. So could be 2x2, could be 3x3, could be 4x4. So you're going to multiply that by another factor of 5 or 6, and so you're getting well over a trillion possibilities, right? Okay.
So all the people would see is like on the right side of the
Yeah,
arrow,
they would
the
just see that
numbers.
string of numbers, and they wouldn't even see it in matrix form. They would just see -26, 69, 86, 7, 41.
Because all the other people would
Okay,
know.
but they know what the encryption matrix is.
Oh.
So they can decrypt it. Okay, here's how they would decrypt it then. Now watch this. This is pretty cool. Question?
Did I just do it by hand?
No. With a calculator or
Oh.
with a computer.
Okay, I was like, that's not fair.
No, that wouldn't be very fun. Okay, so all they're going to do is that's the encryption matrix, right? That I've got highlighted up there?
Yeah.
Okay. Let's just copy that down. So they're going to multiply the inverse of that, right? They want to undo the encryption, so they're going to multiply by the inverse, from the left by the inverse of E, our encryption matrix, their encoded matrix, right? And if they do that, look what they get back. They get back, now this makes sense. Now we know that it's a 3x3 when they get that string of numbers, and so they'd know to read that in, it's going to be, read it in groups of 3, so that would be whatever, what did we say it was, M-A-T-H space I-S space F-U-N space. That is fine, which we all know is true.
So when would you need to know this besides credit card numbers? But that's already in number form. So
Okay, right, so for credit card numbers, you wouldn't even have to do that last. This would just be the string of credit card numbers.
oh.
Yeah. Okay, make sense? That's it. So what you're going to get, here's what your questions look like on the assignment. Did you like that?
We're not gonna have this much overthink.
Yeah, we
Yeah,
are.
we are.
Holy cow, how many times have we gone over this?
James actually was one of those
Yeah.
questions.
And we went over it last week, and we went over it the week
Can we
before.
play the game since we're done?
Sure.
No!